Hi, after talking about how you figured out how many packing peanuts were in the bag, this is something that scientists have been doing for a very long time, and they actually figured it out. So, back when they were not sure, they wanted some sense of, like it says here, how many atoms or molecules were present in a sample they were investigating because they had no idea. And, like they say, the struggle is real, and it certainly was at the time. So what we learned here in Unit 1, way back at the beginning of the year here, is that the density experiment that we saw that we have iron and then we put that in water and massed it as well. And then we also put aluminum in there and we massed it and took the volume of it. And we noticed that the densities for these were different. So why? So there's a couple different possibilities or explanations for that. One model is that the mass of aluminum and the mass of iron are the same, but there's just a little bit more of a number of iron atoms in here than there is in the aluminum atoms in this sample. So they're both the same mass, but, well, there's more iron atoms here than they are in the aluminum. So that's one possibility. You can see that in the picture that's what it is showing. Now, model B. Here's the other possibility. Now, what we could say here is that for 1 cubic centimeter of iron, which this is a lot larger than 1 cubic centimeter, 1 cubic centimeter is 1 centimeter by 1 centimeter by 1 centimeter size. So you're going to have to imagine that. And then we had the same size of this aluminum sample. And what we notice here is that they're the same number of atoms in here, but the size of the individual iron atoms are bigger. So if you look at the pictures there are the same number of circles, but you'll notice that the circles for the iron are a lot larger than the aluminum. So that's a second possibility. So the first one is saying that we end up having the same number in mass. Possibility C is that both the size and the mass of the atoms are different. So that is a possibility as well. So let's take a peek here. So what we notice here is that the particle size does not have an effect on the volume that a given number of gaseous particles occupy. It says the particles are widely spaced out. If you remember that Avogadro's hypothesis, which says if you have a gas at the same temperature and the same volume and the same pressure, you'll have the same number of particles. It has absolutely nothing to do with the actual size of the individual particles. So that's what brings us actually to this counting by weighing topic, is that Gay-Lussac had an experiment that we had actually did. So we had a Erlenmeyer flask, this guy, and then we had a pressure sensor on the top. And what we did is we put this into different temperature surroundings. So we put it in some snow, we put it in hot water, and what we were measuring was the pressure. And so we were not messing around with the volume at all because the volume of this flask was not going to change. Well, you like my nails from tie-dyeing? Anyway, that does not change at all. So what we're noticing is that the particles were not changing. You can notice that Gay-Lussac has a model at the top here that there's no particles in there, but they're saying 1 volume of hydrogen plus 1 volume of chlorine gives you 2 volumes of hydrogen chloride. Well, he didn't know about these particles quite yet. Fast forward to Avogadro, the Amedeo Avogadro. His hypothesis says, again, same temperature, same pressure, same volume, you'll have the same number of particles. And that's what you have here. So we have one molecule of hydrogen plus 1 molecule of chlorine gives you 2 volumes, but in each volume, you notice there's 1 molecule of hydrogen chloride. So that's what we end up having here. If you guys recall doing this, we did this we did this in Unit 4. Then we have another example where we have 2 volumes of hydrogen gas. If you notice in each volume, you have 1 molecule of hydrogen and another volume has another molecule of hydrogen. You add that to or react it with 1 volume of oxygen. If you notice there's 1 molecule yet again in that volume, you'll get 2 volumes, but in each volume, you have 1 molecule of, this case, water. So if you could recall that, we end up dealing with this one yet again. So take a peek at that. But we end up doing weighing by pardon me, start counting particles by weighing them, because these particles are so small. We're unable to weigh one individual one. We're going to be weighing large numbers of them. So just be mindful of that is the direction we're going with this.